What if I told you that this feeling isn't just a paranoid delusion, but a fundamental principle woven into the very fabric of the universe? And what if I told you that the one doing the watching is you? And that your simple act of looking at the world around you fundamentally changes it? This isn't philosophy. This isn't science fiction. This is the deepest, most unsettling, and most exhilarating truth of modern physics. A truth that will take us on a journey from the coldest depths of a laboratory to the furthest reaches of space-time, and ultimately to the very core of what it means to be conscious. Prepare to have your understanding of reality turned inside out, because we're about to dive headfirst into the quantum rabbit hole. And I promise you, the universe you see on the other side will be a universe you never knew existed. Our story begins in a place that seems impossibly remote from our everyday lives, yet is closer to the fundamental truth of reality than anything we will ever experience. We are deep inside a laboratory at MIT, a place of sterile precision, gleaming metal, and the quiet hum of machinery pushing the boundaries of the known. Here, scientists have created conditions colder than the darkest void of outer space. They have isolated individual atoms, the fundamental building blocks of everything you see, and cooled them to a near-perfect standstill. In this extreme environment, they have stripped away all the noise and chaos of our classical world, laying bare the raw, unfiltered, and utterly bizarre essence of quantum mechanics. What they found in a landmark experiment in 2022 confirmed, with chilling and beautiful precision, one of the most profound truths ever discovered. The universe behaves differently when we are looking at it. The very act of observation, of measurement, of gaining knowledge about something, forces it to change its nature. Reality, it turns out, is not a fixed objective stage upon which we are merely actors. Instead, it is a fluid, probabilistic dance, and we, the observers, are its choreographers. This principle is known as wave-particle duality, and it lies at the heart of all quantum weirdness. It's the idea that the fundamental constituents of our universe, the light, that allows you to see this. The electrons that power the device you're watching on, even the atoms that make up your own body are not one thing or the other. They are not simply particles, like tiny billiard balls, nor are they simply waves, like ripples on a pond. They are, somehow, both at once, and neither, until a choice is made. They exist in a ghostly state of pure potential, a shimmering cloud of possibilities. And what forces that cloud to collapse into a single, concrete reality? Our observation. The moment we look, the universe picks a card, any card, and the world we know clicks into place. This single, elegant experiment at MIT was the definitive proof, the final nail in the coffin of our classical intuition. It settled a legendary debate that raged for nearly a century between the two giants of physics, Albert Einstein and Niels Bohr. Einstein, the champion of an objective, hidden reality, famously declared that God does not play dice. He believed that the universe had definite properties, whether we looked or not. Bohr, on the other hand, argued for an observer-dependent reality, a world shaped by the questions we ask of it. The MIT experiment, in its perfect execution, proved Bohr right. The randomness, the uncertainty, the observer dependence of the quantum world are not flaws in our understanding. They are fundamental features of reality itself. To truly grasp the earth-shattering implications of this, we must journey back to the experiment that started it all. A setup so deceptively simple that it can be described in a few sentences, yet so profound that it contains all the mystery of the cosmos. It is called the double-slit experiment. Imagine a solid barrier with two thin parallel slits cut into it. On one side, we have a machine that can fire things. Let's start with something familiar, like tiny paint. We fire them at the barrier, and, as you'd expect, the ones that go through the slits hit a screen behind it, creating two distinct lines, a perfect record of the paths the paintballs took. Simple, predictable, classical. Now, let's switch from paintballs to waves in a water tank. We send a wave towards the barrier. As the wave passes through both slits, it splits into two new waves. These two waves then travel forward, interfering with each other. Where the crest of one wave meets the crest of another, they reinforce, creating a bigger wave. Where a crest meets a trough, they cancel each other out. The result on the screen behind is not two simple lines, but a complex pattern of many lines, a so-called interference pattern. The unmistakable signature of waves overlapping. Again, perfectly logical. But now, let's step into the quantum realm. We'll use a machine that can fire single particles of light, called photons, one at a time. A photon is a particle, a single, indivisible packet of light. Logic dictates that each individual photon must go through either the left slit or the right slit. It cannot go through both. Therefore, over time, as we fire thousands of photons one by one, we should see them build up two distinct lines on the screen, just like the paint. But that is not what happens. As the photons land on the screen, one by one, a dot appears here, then another there, seemingly at random. But as we continue to fire, a pattern begins to emerge from the chaos. And it is not two lines. It is the complex, multi-banded interference pattern of a wave. Let that sink in. The particles, fired one at a time, are behaving like waves. It is as if each individual photon, in its journey, somehow passed through both slits simultaneously, splitting into two waves that then interfered with itself before landing on the screen. This is the first crack in the foundation of our reality. It's as if the universe is telling us that when we're not looking, a particle can be in multiple places at once. Reality, at its most fundamental level, is a haze of probability. This is where the mystery deepens into something that borders on the mystical. The physicists who first saw this result were, understandably, baffled. Their immediate, logical reaction was, we must find out which slit each photon is going through. To do this, they placed a sensitive detector at the slits, a sort of microscopic camera that could register which path a single photon took on its way to the screen. And the moment they did, the impossible happened. The instant the detectors were turned on, the moment the physicists gained knowledge of the photon's path, the interference pattern vanished completely. The photons stopped behaving like waves. They reverted to behaving like predictable, classical particles. They produced two distinct lines on the screen, just like the paintballs. The very act of measurement, the simple act of looking to see which path the particle took, fundamentally altered the outcome. It was as if the universe knew it was being watched and tidied up its act, behaving in a way that made sense to our classical minds. When we don't look, a photon is a wave of possibility, exploring all paths at once. When we do look, it is forced to make a choice, to become a definite particle in a single, definite location. This is the observer effect in its most dramatic and undeniable form. It suggests a concept that is central to the quantum worldview: superposition. Before observation, a particle exists in a superposition of all its possible states at once. It is a wave of potential. It is going through the left slit and the right slit. It is here and there. It is a cloud of every possibility. It is the act of measurement, the interaction with an observing device, that forces this wave of potential to collapse into a single, actualized state. Your look, your measurement, your question, is what forces reality to commit to an answer. You are not a passive bystander. You are an active participant in the ongoing creation of the cosmos. This mind-bending revelation wasn't discovered overnight. It was the culmination of a debate that raged for over 300 years. a battle of ideas between some of the greatest minds in scientific history. The story of wave-particle duality begins in the late 17th century, with a monumental intellectual duel. On one side was the towering figure of Sir Isaac Newton, who argued forcefully that light was made of tiny particles, which he called corpuscles. His reasoning was simple. Light travels in straight lines and casts sharp shadows, just like a stream of tiny bullets. On the other side was the brilliant Dutch physicist Christiaan Huygens, who proposed that light was a wave. He argued that a wave nature could better explain phenomena like refraction, the bending of light as it passes from air into water. For over a century, Newton's immense prestige held sway, and the particle theory reigned supreme. Then, in 1801, a British polymath named Thomas Young performed the original double-slit experiment, shining light through to pinholes and revealing for the first time the undeniable interference pattern, the smoking gun of wave behavior. The scientific community was stunned. The debate seemed to have been settled in favor of waves. This view was solidified later in the 19th century by the work of James Clerk Maxwell, whose elegant equations described light as an electromagnetic wave. For a while, it seemed the mystery was solved. Physicists breathed a collective sigh of relief, believing they had finally captured the true nature of light. But the universe had another surprise in store. A nagging anomaly, a small, unexplained phenomenon called the photoelectric effect, refused to fit the perfect wave theory. This single stubborn fact would change everything, reviving a debate that would tear physics apart and redefine our understanding of reality itself. The year is 1905. A young, unknown patent clerk in Bern, Switzerland, named Albert Einstein, publishes a paper that will ignite a revolution. In it, he tackles the photoelectric effect, the observation that shining light on a metal surface can knock electrons loose. According to the classical wave theory, a brighter, more intense light should give the electrons more energy, but experiments showed this wasn't true. Instead, the energy of the electrons depended only on the light's color, its frequency. A dim blue light could knock electrons loose, while an intensely bright red light did nothing. Einstein's explanation was as simple as it was radical. He proposed that light wasn't a continuous wave after all, but was composed of discrete, particle-like packets of energy. He called these packets light quanta, which would later be named photons. Suddenly, the paradox was solved. The energy of each photon was tied to its frequency, not the intensity of the light. This brilliant insight proved that light, which Young and Maxwell had so convincingly shown to be a wave, also behaved as a particle. Einstein had not resolved the old debate. He had made it infinitely more paradoxical. Light was somehow both a wave and a particle. This impossible contradiction only deepened a few years later, when a French prince and physicist, Louis de Broglie, made an even bolder proposition. He suggested that if waves of light could act like particles, then perhaps particles of matter like electrons, atoms, and even, in principle, baseballs and people, could act like waves. It was a breathtaking leap of intuition, a perfect expression of cosmic symmetry. And incredibly, it was soon proven true by experiments that showed beams of electrons creating the same kind of interference patterns as light waves. The world of physics was now faced with an undeniable, logic-defying duality at the heart of all matter and energy. How could something be two opposite things at once? It fell to the great Danish physicist Niels Bohr to offer a way out of this philosophical dead end. He proposed a radical new idea called the principle of complementarity. Bohr argued that the wave and particle aspects of reality are not contradictory, but complementary. They are like two faces of the same coin. You can see one side or the other, but never both at the same time. The aspect of reality we get to see, Bohr claimed, is determined entirely by the type of experiment we choose to perform. If you set up an experiment to look for a particle, you will find a particle. If you set up an experiment to look for a wave, you will find a wave. The choice is not nature's. It is ours. This was the observer effect, now elevated to a core principle of the universe. At this point, you're probably asking a very reasonable question. If all this quantum weirdness is happening all the time, why don't we see it in our everyday lives? Why don't we see baseballs acting like waves and being in two places at once? The answer lies in a crucial concept called quantum decay. Think of a quantum system, like our single photon, as being incredibly delicate and shy. Its wave-like superposition is a fragile state of being. Decoherence is the process by which this quantum fragility is lost through interaction with its surroundings. Any interaction, no matter how small, a stray photon bouncing off it, a single air molecule bumping into it, or, crucially, a measuring device placed in its path, can cause the system to lose its quantum coherence and decohere into a definite classical state. In essence, an observation doesn't require a conscious human mind staring at an experiment. It simply requires an interaction with the environment that carries away which path information. The universe is a very noisy and busy place. The objects in our macroscopic world are constantly being bombarded by trillions upon trillions of particles every nanosecond. This constant interaction with the environment effectively constitutes a continuous measurement, instantly collapsing any potential quantum superpositions before they can ever become noticeable. This is why a cat is always either alive or dead, and a baseball is always in one place. They are simply too big and too connected to the world to maintain their quantum secrets. However, decoherence, as elegant as it is, only provides a partial answer. It explains why we don't see quantum weirdness in big things. It explains the transition from a quantum superposition to a classical set of probabilities. But it doesn't solve the deepest mystery of all, the so-called measurement problem. Decoherence tells us that a quantum system will settle into one of its possible states, but it cannot tell us why we observe one specific outcome out of all the possibilities. When we look at the photon, why does it land right here and not a millimeter to the left? The theory says there was a probability for it to be in either place, but it offers no explanation for why one reality was chosen over another. This mystery of why measurement forces a definite outcome remains one of the greatest unsolved puzzles in all of science, a frontier that pushes the boundaries between physics and philosophy. If you thought reality couldn't get any stranger, hold on tight. The quantum world's disregard for our classical intuition extends to its very relationship with time itself. We tend to think of time as a one-way street. The past is fixed, the present is what's happening, and the future is unwritten. Cause precedes effect. But in the quantum realm, this linear understanding of time begins to break down in spectacular fashion. This is demonstrated most mind-bogglingly in experiments known as delayed choice experiments, first proposed by the legendary physicist John Archibald Wheeler. Imagine our double-slit setup, but with a twist. We make the decision whether to place detectors at the slits, and thus measure the photon's particle nature after the photon has already passed through the barrier. Think about what this means. According to our classical understanding, the photon has to decide whether to behave like a particle going through one slit, or a wave going through both slits at the moment it encounters the slits. But, in this experiment, our choice to observe its path happens in the future, long after that moment has passed. Incredibly, the results show that this future choice retroactively determines the photon's past behavior. If we choose to look, the photon will be found to have behaved like a particle all along. If we choose not to look, it will have behaved like a wave. It's as if our present actions are reaching back in time to change a historical event. Taking this even further are the truly bizarre quantum eraser experiments. In these setups, information about the particle's path is first recorded, which, as we know, destroys the wave pattern. But then, at a later stage, that information is erased through another clever quantum measurement. And when the witch path information is erased, the interference pattern miraculously reappears in the data, as if the path was never known in the first place. A measurement performed in the future can retroactively change the historical record. A photon that was recorded as a definite particle can become a wave again, all because of something we chose to do later on. These results are not speculation. They are confirmed experimental facts. They suggest that our deeply ingrained, linear view of cause and effect is nothing more than a classical illusion. At the quantum level, the past, present, and future are entangled in a way we are only just beginning to comprehend. The past may not be as fixed as we think, and our present observations might just be participating in the creation of cosmic history itself. So, if reality is not made of solid, predictable things, and if even time doesn't flow in a straight line, what is the universe actually made of? Quantum mechanics pushes us towards a radical and profound answer. At its deepest level, the universe is made of information. Think about the phenomenon of quantum entanglement, which Einstein famously called spooky action at a distance. When two particles are entangled, they form a single, unified quantum state, no matter how far apart they are. If you measure a property of one particle, you instantly know the corresponding property of its partner, even if it's on the other side of the galaxy. This connection is instantaneous, faster than the speed of light. But it's not a physical force or a signal. What connects them is shared information. Their information exists as a single, non-local entity, spread across space, yet unified. Quantum field theory takes this idea even further. It describes the universe not in terms of particles, but as a collection of fundamental fields that permeate all of space and time. A field for electrons, a field for photons, and so on. What we perceive as a particle is simply a localized vibration, an excitation, in its underlying field. From this perspective, even a perfect vacuum-empty space is not empty at all. It is a seething, bubbling sea of virtual particles that constantly pop in and out of existence, a fabric of pure potential, generating measurable forces. In this informational universe, wave-particle duality is no longer a paradox. It's simply two different ways that information can manifest and be read by our instruments. When we don't constrain the system, the information exists as a distributed, wave-like potential. When we perform a measurement, we localize that information, forcing it to manifest as a particle-like event. Reality, in this view, is a vast network of information, and the laws of physics are the rules governing how that information is processed and transformed. The world of solid objects is a secondary phenomenon, an emergent property of a much deeper, more abstract informational reality. These mind-bending mysteries are no longer confined to the chalkboard of a theoretical physicist or the hushed environment of a laboratory. They are now the foundation of a technological revolution that is poised to reshape our world. We are harnessing the strangest aspects of quantum mechanics to build technologies that were once the stuff of dreams. The most prominent of these is the quantum computer. Classical computers, from your smartphone to the most powerful supercomputers, work with bits that can be either a 0 or a 1. A quantum computer, however, uses qubits. Thanks to the principle of superposition, a qubit can be a 0, a 1, and both at the same time. By linking qubits together through entanglement, a quantum computer can explore millions of possible solutions to a problem simultaneously. This promises to solve problems in medicine, finance, materials, science, and climate change that are completely intractable for even the fastest classical machines. Imagine designing new life-saving drugs, molecule by molecule, or creating perfectly efficient new materials for solar energy, or cracking the complexities of the global climate system. This is the power that quantum computing unlocks. Meanwhile, the observer effect is the principle behind a new form of perfectly secure communication, quantum cryptography. The idea is elegantly simple. Information, like a secret key for encryption, can be encoded in the quantum states of photons. If an eavesdropper tries to intercept and measure these photons to steal the key, their very act of measurement will disturb the quantum states in a detectable way. The observer effect, once a philosophical puzzle, becomes the ultimate burglar alarm. This technology is not theoretical. It is already being implemented to create unbreakable communication networks for governments, banks, and critical infrastructure. These technologies are powerful proof that the weirdest features of our universe are also its most potent resources. The quantum revolution is now extending beyond physics and technology, and into the very heart of biology. For the longest time, it was assumed that the warm, wet, chaotic environment of a living cell was the last place you'd find the delicate and fragile effects of the quantum world. But stunning new evidence is revealing that life itself may have evolved to harness the secrets of the quantum realm for its own advantage. The most compelling example is photosynthesis, the process that powers nearly all life on Earth. When a particle of light from the sun strikes a leaf, its energy must be transported with incredible speed and efficiency to a reaction center, where it can be converted into chemical energy. Classical physics cannot fully explain the near 100% efficiency of this energy transfer. A classical system would lose much of that energy as heat. But evidence now strongly suggests that photosynthesis uses a quantum trick called quantum coherence. The energy from the photon doesn't travel down one single path. It travels down all possible paths at the same time, in a state of superposition. This quantum search allows it to instantly find the most efficient route to the reaction center, a feat no human-designed solar cell can even approach. This discovery is transformative. It challenges our view of biology as a purely classical, mechanical process. It suggests that life, far from being oblivious to the quantum world, has evolved sophisticated mechanisms to protect and exploit these delicate quantum effects. And if quantum mechanics is crucial for something as fundamental as photosynthesis, where else might it be hiding? In the way birds navigate using the Earth's magnetic field, in our sense of smell, or in the most complex and mysterious biological system of all. We now arrive at the deepest and most speculative part of our journey, where the quantum rabbit hole opens into the vast and mysterious territory of the human mind. If quantum processes are essential for life, could they be the key to unlocking the greatest scientific mystery of all, the nature of consciousness itself? This leads us to the quantum consciousness paradox. The argument goes something like this. The brain, with its billions of interconnected neurons and trillions of synapses, is the most complex quantum system we know of. What if consciousness is not just an emergent property of classical neural computations, but is instead a macroscopic quantum phenomenon? Some theories, like the controversial but intriguing ORCO, are theory by Sir Roger Penrose and Stuart Hameroff, propose that quantum computations happening within the microscopic protein structures of our neurons, called microtubules, could be the physical basis for conscious moments. Now, connect this with what we've learned about the observer effect. If the act of observation is what collapses the quantum wave function and brings reality into a definite state, and if consciousness is required for there to be an observer, we are faced with a mind-bending loop. If the brain's quantum processes create consciousness, and consciousness is required to collapse quantum states into reality, then mind and reality may be locked in an inseparable, self-creating circle. This perspective offers radical new ways of thinking about ourselves. Could memory be stored in the entangled quantum information of the brain? Could what we call free will be the result of our conscious choice collapsing the quantum probabilities of our own neural states? Could our very identity be a continuously collapsing wave function? This is the frontier where physics, neuroscience, and philosophy meet, suggesting that our consciousness might not be a mere accident of evolution, but a fundamental participant in the quantum nature of the universe. As we stand on the precipice of this new understanding, we are also approaching a new phase of evolution, one where human consciousness could directly merge with the artificial quantum systems we are building. The development of advanced quantum computers and increasingly sophisticated brain-computer interfaces opens the door to a future of hybrid intelligences that could transcend the limitations of both biology and classical technology. Imagine an awareness that is not confined to a single train of thought. Imagine a mind that can harness the power of superposition to explore countless ideas, solutions, and creative pathways simultaneously, holding multiple contradictory thoughts in perfect harmony until a conscious choice is made. Picture the possibility of human minds becoming entangled with one another, allowing for the direct sharing of thoughts, emotions, and experiences without the clumsy medium of language. This future would undoubtedly transform society in ways we can barely conceive. It could accelerate scientific discovery, create unimaginable art, and perhaps even solve the deepest problems of human conflict. But it also raises profound and urgent questions about what it means to be human. If our minds are linked and our thoughts are no longer private, what happens to individuality? If our consciousness can be uploaded and merged with a machine, where does the self begin and end? The quantum revolution is not just changing our technology. It is forcing us to confront the very definition of ourselves, as the boundaries between mind, machine, and the fabric of reality begin to dissolve. Let's return, for a moment, to those baffling experiments that seem to rewrite the past. The delayed choice and quantum eraser experiments shatter our most cherished intuition, the linear, forward flow of time. They suggest that the past is not a fixed, immutable record, but is somehow malleable, still in conversation with the present. This leads to one of the most mind-bending possibilities in all of science. Our universe may be fundamentally timeless. Just as quantum entanglement links particles across vast distances of space, physicists are now exploring the idea of time-like entanglement, where particles can be correlated across time. This suggests that the past, present, and future might not be a sequence of moments that happen and then disappear. Instead, they might coexist as a single, static, timeless quantum information structure, what some call the block universe. In this view, what we experience as the flow of time is an illusion, a product of our consciousness. Imagine a movie on a reel of film. All the frames, the beginning, the middle, and the end exist simultaneously on the reel. The story only unfolds when the light of the projector, our consciousness, moves through the frames one by one, creating the experience of a linear narrative. What if our consciousness is simply navigating through this timeless reality, creating a sequence of events, a personal timeline, through its continuous choices of what to observe? In this radical view, consciousness doesn't exist in time. It creates the experience of time. We are not just participants in creating reality, but in creating the very flow of history itself. Our journey has taken us from a single experiment in a frigid laboratory to the very edge of reality, time, and consciousness. And it all leads to a single, breathtaking, and deeply empowering conclusion, articulated beautifully by the physicist John Archibald Wheeler. We live in a participatory universe. The universe is not a cold, dead, clockwork machine that we passively observe from the outside. We are not separate from the reality we study. We are inextricably woven into its fabric. Wave-particle duality is the ultimate proof of this cosmic partnership. It shows us that reality, at its core, remains a shimmering sea of infinite possibility until an observer, an entity capable of interacting and gaining information, looks. That act of looking, of measuring, of participating, is what transforms potential into actuality. As Wheeler poetically described it, the universe can be pictured as a giant U-shape, starting with the Big Bang, evolving over billions of years, and eventually giving rise to observers like us. We, at the other end of the U, can then look back, observing the light from distant galaxies and the cosmic microwave background radiation. And in doing so, we bring the universe's long history into definite being. We are the universe becoming aware of itself. Through every act of observation, from a physicist in a lab to you simply looking at the world around you. We are active participants in the grand cosmic dance that solidifies the fabric of reality. So, what does all of this mean for you in your daily life? How can these strange, abstract ideas from the quantum realm possibly apply to the world of jobs, relationships, and personal growth? The connection is more profound than you might think. While we may not be able to consciously decide whether a car is a wave or a particle, we can apply the deep lessons of quantum mechanics metaphorically to transform the way we experience our own reality. First, the observer effect teaches us the incredible power of our focus and attention. Where you place your attention, reality bends. Just as observing a photon forces it to choose a state, the things you consistently focus on in your life, your goals, your gratitude, your fears are the things that will manifest more strongly in your reality. You are constantly collapsing the wave of infinite possibilities that is your life into the actuality of your experience. Choose wisely what you observe. Second, the principle of superposition reminds us that until we make a choice, we exist in a state of pure potential. Before you decide you can't do something, you exist in a superposition of succeeding and failing. Before you label an experience as good or bad, it is simply what is. Embracing this uncertainty, this state of open potential, is the root of all creativity and growth. It allows you to explore multiple paths without being locked into one, to see problems not as fixed obstacles, but as clouds of possibility waiting for a new observation. Finally, the participatory universe tells us that we are not victims of circumstance, but co-creators of our world. We are not separate from the universe. We are a fundamental part of its process. This understanding dissolves feelings of helplessness and isolation. It empowers you to know that your choices, your observations, and your very consciousness matter on a cosmic scale. You are a ripple on the surface of a vast ocean, distinct yet inseparable from the whole. The journey into the quantum realm is a journey back to ourselves. It shows us a universe that is more mysterious, more interconnected, and more participatory than we ever dared to imagine. It asks us to let go of our rigid, classical certainties and embrace a world of possibility, a reality that is waiting for us to look at it, to engage with it, and to help bring it into being. So I leave you with a few questions to ponder. If your observation truly shapes your reality, what have you been choosing to observe in your own life? What interference patterns have you been creating with your thoughts and beliefs? And what new possibilities could you collapse into reality simply by choosing to look for them? Thank you for joining me on this incredible journey. I wish you all good health, a clear focus, and a life filled with wonderful possibilities. And if you found this exploration of reality as fascinating as I do, please don't forget to like, share, and subscribe to the channel for more journeys into the deepest mysteries of our universe.